Hello and welcome. Today we are diving into something that, believe it or not, affects pretty much every piece of advanced tech you own. I'm talking about your gaming PC, your phone, even the massive supercomputers that power our world. We're talking about heat and the absolutely incredible microscopic science of how we get rid of it.
So, here's the fundamental issue. For decades, we've been on this relentless mission, right? Make our electronics smaller, faster, more powerful. But there's a catch. A law of physics that's becoming a huge roadblock. All that amazing power generates a ton of heat in a space that's getting smaller and smaller. And to really get a grip on just how big this problem is, look at this number. Future microchips are expected to crank out heat at 300 watts per square centimeter. Now, what does that even mean? Well, imagine taking the heat from 3 big, old-school 100-watt light bulbs and cramming all of it onto a surface the size of your pinky nail. It's an absolutely insane amount of energy we need to somehow get rid of.
So, how in the world are scientists and engineers supposed to solve this thermal crisis? Well, here's our roadmap. We're going to start with the microheat problem itself, then look at a wild solution that involves boiling liquid in tiny little tubes. After that, we'll see how you can even simulate something you can't see, the tough challenges that come with that, and finally, what all this means for the future of cool tech.
Okay, so let's start with something we can all relate to, right? That feeling when your laptop starts getting a little too toasty on your lap. Now, just try to imagine that exact problem, but amplified 1,000 times over, all happening on the tiny scale of a microchip. You see, the ways we have always cooled things, fans, big metal heat sinks, they're just hitting a wall. They can't keep up anymore. And this thermal bottleneck, as they call it, isn't just an annoyance. It's a hard limit on how powerful our technology can ever get. We seriously need a whole new way to think about cooling.
And that brings us to a really fascinating solution, one that honestly sounds a little counterintuitive at first. We're going to use boiling to cool down our hottest electronics. The process is called flow boiling, and the idea behind it is kind of genius. You pump a liquid coolant through channels that are literally smaller than a human hair. As that liquid zips past the superhot surface of the chip, it boils. It instantly flashes from a liquid into a vapor. And that phase change, that transition, absorbs a massive amount of heat energy. It's called latent heat and just carries it away. And right here, you can really see the difference. Conventional cooling is what we call single phase. It's just liquid flowing around, soaking up some heat. But flow boiling, that's two-phase. By harnessing the raw power of evaporation inside these tiny little tubes, it can pull away orders of magnitude more heat. Think about it. It's the difference between just warming up a pot of water versus the massive energy it takes to actually boil that water away into steam. Okay, this all sounds amazing in theory, but it creates a whole new massive challenge. We're talking about bubbles and vapor in channels that are just a few dozen micrometers wide. So how could you possibly study that? How do you measure it? How do you perfect it? This is the big question. This is what moves the research out of the physical lab and into the digital world. I mean, you can't just stick a tiny thermometer in there and see what's going on with the bubbles. The very act of trying to look at it would completely change what's happening. The answer is, you build a perfect digital twin. Scientists use this incredibly powerful tool called Computational Fluid Dynamics, or CFD for short. You can think of it like a weather forecast, but instead of predicting storms in the atmosphere, it's predicting the flow of fluids, the birth of bubbles, and the transfer of heat inside a virtual microbe tube. But wow, creating this virtual world is just unbelievably complex. Researchers have a whole toolbox of different mathematical methods just to track that super important, constantly changing boundary between the liquid and the vapor. All these different methods are trying to do the same thing, draw that invisible line between water and steam as perfectly as possible. But, like with any simulation, getting the details right is ridiculously hard. Trying to build a virtual bubble that acts exactly like a real one at this microscopic scale, well, that's one of the biggest challenges in this whole field. And check out this quote from one of the papers. It really gets to the heart of the problem. Sometimes the math itself creates these phantom effects. Imagine trying to simulate a perfectly still drop of water, but your simulation starts showing these tiny, invisible whirlpools inside of it. Those are spurious currents. They're like mathematical ghosts that aren't there in the real world, and they can completely throw off your results. So to make these simulations actually work, researchers have to tackle all these huge hurdles. They have to perfectly model surface tension, which is a massive force at this tiny scale.
They need to predict exactly how bubbles are born, how they grow, how they merge together, and they have to hunt down and get rid of those pesky spurious currents to make sure their virtual world is a true reflection of the real one. So you might be asking, why go through all this trouble? Why spend so much time and computing power on virtual bubbles? Well, because mastering this technology isn't just some cool science project. It's the key that's going to unlock the next wave of technological innovation. I mean, the applications here are just staggering. We're talking about everything from the next generation of super-fast CPUs and GPUs to critical systems in aircraft and spacecraft. This kind of tech is going to be absolutely essential for things like managing heat and powerful EV batteries. It could completely revolutionize efficiency in all kinds of industrial settings. Getting this right is literally about enabling the future. And that really brings us to our final thought. For decades, we've been in this race to push computing power forward. But running right alongside it has been another, quieter race. The race to manage the heat that all that power creates. And as we push closer and closer to the absolute physical limits of silicon, the solutions will have to be just as clever and just as microscopic as the chips themselves. The future isn't just about getting faster, it's about getting cooler. Thanks for joining me.